morning, everyone. We are Team 2, and our project is an Origami Engineering homeless shelter. The team consists of myself, Martina, Noor, and Joseph. A quick overview of what we'll be talking about today. First, a quick about the project. Next, the background research that went into it, our science and technology, our testing and validation, our project stages, and our conclusion. So just to start, the abstract, due to the rapid gentrification that's been occurring across the United States, there's been an increase in homelessness and poverty. And to tackle this problem, we created a portable origami homeless shelter that can provide a temporary and safe space for individuals. So with that, we exactly want to deliver is to develop a multi-layered portable homeless shelter that can withstand facets of weather, as well as it's lightweight and foldable to be easily transported. Our background research. Currently out there on the market, there's past designs, but they're comprised solely of cardboard and were not portable, with the weather. And many are clunky and live in eyesore to the community, unfortunately. And there are other variations out there, such as plastic tents, but many include an air pump, which is just not feasible, and they do not include aspects such as portability and rigidness, which we were trying to solve. So our motivation for this project, there's an average of 552,000 people who are homeless in the United States, and life expectancy on average is only 50 years old. 17 per 10,000 people experience homelessness each day, and 70% of those homeless people are under the age of 50. And 0.2% of Americans, I'm sorry about that, 0.2% of Americans live in the state of homelessness, and 13,000 homeless people die every year.
So now for the science and technology aspect of it, for our model design, we wanted to do something that was durable, non-biodegradable, washable, easy to clean, foldable, lightweight, inhibits odor, mold, and is weather resistant because obviously homeless people are always on the move. And due to COVID, we needed something that was sanitary and can be carried from one location to another. Next slide. So for the top 3 things that we wanted in our optimal materials, we chose that it needed to be weather resistant, insulated, and foldable so that it could withstand different weather conditions, be portable, and then the shelter itself would remain insulated. So for configuring the optimal combination, we ordered over 20 materials and glued and stapled them together so that we can test which combination was the best for the materials. As far as machinery went, in the beginning of the semester, we did use Dr. El-Sayed's 2 folding machines, but due to unforeseen circumstances and the lack of technicians, we actually ended up not using these final machines for our final prototype, but they did help in coming up with the original folding aspect of the prototype. This is a CAD Rhino model that we originally came up with and that Joe will discuss more later on of what we wanted the final model to look like. The current dimensions of the prototype are 42 by 24 by 12, and the weight is around 2 pounds. So for the proposed final design, we wanted to double all of these measurements so that it could be kind of universal and be comfortable for people to sleep in. And then the last part of it was a technological component, which was going to be an added safety feature. So we decided that when we would give out these tents, we would also connect them with Assurance wireless phones, which are actually free government Lifeline assistant phones. They have unlimited data, text, minutes, and gigabytes. And the qualifications for getting one is typically for those who are in public assistance programs or are unemployed, so homeless individuals can receive them for free.
As for the testing and validation for our project, we took these 20 materials and the first thing that we did was put it in a humidity machine. So we were able to observe how it reacts in heat and really high humidity and also in the cold. So result for this machine is that the longer we kept it in there, we saw the number of materials being affected more. The top 2 things that affected the materials was the humidity and the cold. So the next test that we did is a water and tear testing. So the two pictures to our left is we took all the materials and we absorbed them in water. And the next day we were able to test its resistance, its water resistance, and be able to determine the best materials that reacted that well. And then the two pictures to our right, we were being able to test the strength and durability of each product and seeing which one was the most rigid. So to conclude, after doing all this testing, we found our final materials. So for our bottom layer, we used a polyurethane coated nylon, and this was the most durable and water resistant fabric. But it was also very lightweight and flexible, which is really important in having that portability aspect of our project. And then for our structure, we used Tyvek paper, Velcro, and concrete wire. So again, this was very lightweight, durable, breathable. Yet it had this resistance to water, abrasion, bacteria penetration, and aging. And then for our outer layer, we used polyethylene sheeting. Again, it proved to be the most durable and rigid in all of the testing that we did.
The final stages of our project, we've started off brainstorming ideas for possible designs and a direction to take for our project. The next step was market research to find possible solutions, see if there's any other designs out there that would resemble our own. The next step was testing the waterproofness of different materials, durability in the cold, and its behavior in the heat. And the final step was actually constructing our design. And here we have a demo of Devin and I putting together our design. Next slide. So continuing our project past this presentation, it is important to us. So this is how we're going to strive forward. We're going to continue to test materials to see if we can possibly find something better than what we have now. Create a human-sized model and do human testing. We would also like to connect with the continuum of care to help distribute our design. Social service programs, connect with homeless individuals, and hopefully in the end help homeless people find permanent housing, given that our design is only a temporary solution. And in conclusion, possible long-term impact of our design could help provide temporary shelter for people experiencing homelessness, and can help those with mental health issues or possible substance abuse problems. We could provide a shelter that can help decrease illness from improved sanitary conditions. And in the future, our efforts will be geared towards transitioning users of our product into more permanent housing and help them get in contact with essential recovery support. Thank you, everyone. Special thanks to Dr. Jafari, Dr. El Sayed, John Rich, and Ashley Kopp.